Hello everyone, this is lecture 15, chain rules. In the last lecture, we have talked a little bit about chain rule when you take the partial derivative of the function with respect to just one variable. And that chain rule that we talk about in lecture 14 is very similar to the idea of chain rule when you talk about single variable calculus. Now, in this lecture, we're going to combine the idea of chain rule in single variable calculus with the idea of partial derivatives to develop a new method for finding derivatives of function of several variables. So the difference between the chain rule and the one that we apply in lecture 14 is that you have one dependent variables and two independent variables, x and y, and the independent variables will depend on another parameter t or two parameters u and v. So it's get quite complicated when you talk about finding the partial derivative of the function with respect to the parameter t or u or v for that matter. To illustrate the importance of this method, we're going to consider the following situations. So economists modeling manufacturing system often work with production functions that relate the productivity or the output of the system to all the variables on which it depends, which is the input. A simplified production function might take the form of, let's say, P equal to F of L, K, and R, where L represents the availability of labor, K is the capital, and R is the natural resources. However, the variables L, K, and R may be intermediate variables that depend on other variables. For example, it may be that L is a function of unemployment rate, let's say U. K is a function of prime interest, little I, and R is a function of time, little t, which is the seasonal availability of resources. Even in this simplified model, we see that the productivity, which is dependent variable, is ultimately related to many other variables. So the critical interest of an economist in this situation is how changes in one variable determine changes in other variables. For instance, if the unemployment rate increases by 0.1% of the interest rate, and the interest rate decreases by 0.2%, what is the effect on productivity? Something like that to motivate the idea of this section. So hopefully at the end of this lecture, we could be able to state chain rules for one or two independent variables. Right? And the context of independent variables in this case is the idea of parameters. And also we could be able to perform implicit differentiations of function of two or more variables. Before I jump into the detail of the formula, how to find the partial derivative of the function with respect to one parameter or one independent variable for that matter, I'm going to revisit the chain rule of a composite of two functions. That is, if you want to find the derivative of the functions, f of g of x. So f of g of x is called the composite functions, where you have f is the outside function and g of x is the inside function. The derivative of this composite function is equal to the derivative of the outside functions, evaluate at the inside functions, multiply with the derivative of the inside functions. So that's the basic that we learn in single variable calculus. Now we move on to more complicated situations. In this case, you have that x is equal to g of t and y is equal to h of t are differentiable functions of t, and z is equal to f of x comma y. So in this case, you see that z is the function of two independent variables, but each independent variable depends on the parameter t. Therefore, this is the situations of functions of one independent variable. So the context of independent variable in this situation is the parameter of considerations. The function z equal to f of xy is differentiable functions of x and y. Then z equal to f of x of t, comma y of t is a differentiable function of t. And to find the differentiable function, we're going to do dz dt equal to partial z partial x times dx dt plus partial z partial y times dy dt. Now the notations look a little bit off here because you have different notations in the formula, but that is the intentions of the formula. So you want to find the derivative of the functions with respect to t, right? This is composite functions because z depends on x and y depend on t. So therefore you take the derivative of the outside function multiply with the derivative of the inside functions. Here in this case, because you have two variables, x and y, therefore you have to add another terms here to indicate that you want to take the derivative of the outside functions, then multiply with the derivative of the inside functions. Now, the reason for the different notations here is that z is the function dependent on x and y, therefore you have to use the partial derivative notations. Whereas x is the function depends on t only, so you use the regular derivative. Similarly, in this case, for z is the functions of x and y, therefore the partial derivative notations. Whereas y is a function depends on t only, therefore the regular derivative. Here's the tree diagram to show how we can get the formula for the chain rule of one independent variable. So that is z is the functions of f of x comma y, where x is equal to x of t and y is equal to y of t. So that is x is the function in terms of t and y is the function in terms of t as well. When you take the partial derivative of z with respect to x, you have to use partial derivative notations. So here you have partial z, partial x. Similarly, you have partial z, partial y. And when you want to take the derivative of x with respect to t, because x only depends on t, so you use the regular derivative. That is dx dt, and here is dy dt. And you combine everything together to arrive at the chain rule of the function of one variable. In this case, again, the one variable I said is the parameter t. So you have dz dt is equal to partial z, partial x, multiplied with dx dt plus partial z, partial y times dy dt. So that's the formula, and we're going to apply this formula to some example. So in the first example here, you want to calculate dz dt of the function z equal to f of xy equal to 4x squared plus 3y squared, where x is a function of the parameter t. In this case, x is equal to sine of t, and y is also a function of the parameter t, where y of t is equal to cosine of t. So you're going to apply the formula that is dz dt equal to partial z, partial x times dx dt plus partial z, partial y times dy dt. So we have four terms that we need to take care of. That is partial z, partial x, dx dt, partial z, partial y, and dy dt. And we're going to work on these terms separately, and then we're going to plug in the result into the formula later. So here you have partial z, partial x. Right, so that is the first order partial derivative of z with respect to x. In this context, you treat y as a constant and you take the derivative with respect to x only. So you have partial x of 4x squared plus 3y squared. That is, you have 4 times 2x plus 0 because the partial derivative of 3y squared with respect to x is equal to 0. Here you get 8x for the answer of partial z, partial x. Now for dx dt, you take the regular derivative of x with respect to t, and x is equal to sine of t, so the derivative of sine of t is cosine of t. Similarly, you have partial z, partial y is equal to partial y of 4x squared plus 3y squared. Again, in this context of partial derivative of the function with respect to y, you treat x as a constant and you take the derivative of the function with respect to y only. So the derivative of 4x squared is going to be 0 plus the derivative of 3y squared is going to be 3 times 2y, or this is 6y. And for dy dt, you take the regular derivative of y with respect to t, that is the derivative of cosine of t, or this is negative sine of t. Now you have all the information that you need. Plug all the information into the formula. We're going to get that dz dt is equal to partial z, partial x, which is 8x, times dx dt, which is cosine of t, plus partial z, partial y, which is 6y, times dy dt, which is negative sine of t. However, we are not finished yet. The idea is that we want to write the result in terms of the parameter t. So we're going to rewrite x in terms of t and y in terms of t. That is x equal to sine of t and y is equal to cosine of t. So 8 times sine of t times cosine of t minus 6y So minus because you have a negative upside of t here. So minus 6y or minus cosine of t times sine of t. And these two are like terms, so you combine them together and you get 2 times sine of t cosine of t. You can stop right here, but you can take one more step further. This is a strict identity, this is the double angle formula, and I'm going to get this to be sine of 2t. So that's how you arrive at the answer in finding the derivative of the function using chain rule for function of one variable. Another way to look at this problem is that you can first substitute x equal to sine of t and y equal to cosine of t into the function. Now the function z depends on t only. So what do I mean by that? So you can do z equal to 4 times sine squared of t plus 3 times cosine squared of t. And then you take the derivative of the function with respect to t directly. Okay, and you should arrive at the same answer. However, as you can see, it's look a little bit more complicated compared to what we have done so far. Even though the step may take a little bit longer, it's just that we could be able to break the problem down into multiple steps, which make the problem solving a little bit easier. Okay, so I'm going to move on to the next example. So it's very similar to example 1, that is, you want to find the z/dt of the function z equal to x squared y plus 3xy to the 4, where x is equal to sine of 2t and y is equal to cosine of t. So to find the derivative of the z/dt, you do partial z partial x times dx dt plus partial z partial y times dy dt, where partial z partial x is equal to 2xy plus 3y to the 4th. So I'm going to skip a lot of steps here, and hopefully at this point you are comfortable with taking the partial derivative of a function with respect to x or to y. Now for dx dt, you're going to get cosine of 2t times 2, or just 2 times cosine of 2t. And for partial z partial y, this is going to be x squared plus 12x times y cubed. And for dy dt, you get this is equal to negative sine of t. Now you have all the information that you need. Substitute this into the formula dz dt. Then we have that dz dt is equal to 2xy plus 3y to the 4th times 2 cosine of 2t plus x squared plus 12xy cubed times negative sine of t. The result of dz dt has to be in terms of t. Therefore, you're going to replace x by sine of 2t and y by cosine of t. So we get 2 times sine of 2t times cosine of t plus 3 times cosine to the 4th of t times 2 cosine of 2t plus sine square of 2t plus 12 times sine of 2t times cosine to the 3rd power of t, and then multiply with negative sine of t. Okay, so that is the result. It's quite complicated, but actually we achieve our objective. That is, can you find a dz dt given the function f of x, y, and x is in terms of t and y is also in terms of t.